Sorry, it's me. Alright, good afternoon. Sorry I can't be there with you guys today. So today we're going to start chapter 7, a whole new set of functions today. So moving away from trigonometry, moving into exponential functions. These types of functions you guys have probably seen already in one form or another. I think I remember talking about it in Science 10 when we talked about radioactive half-lives. If you don't remember from Science 10, you'll probably have seen it in Chemistry 11, talking again about radioactive half-lives. You'll probably see it again in Physics 11 with, again, more radioactive half-lives. In biology, you might have dealt with it in terms of bacterial population growth, all good examples of exponential functions. If any of you have done any kind of game development, exponential functions are also very handy for any kind of leveling up algorithm. Alright, so those are some examples of what an exponential function can be used for. So it's actually kind of a useful function to know. Now, an exponential function looks as follows. The basic exponential function, which is what we're going to be dealing with for today, transformed exponential functions we'll deal with tomorrow, but basic exponential functions look like this. F of x is equal to c to the power of x. C is just any number greater than 0. We won't get into too much detail as to why it has to be greater than 0. One of your assignment questions actually takes you through that. A couple characteristics for the basic exponential function is that if c is greater than 0, the function is increasing, so it's always going up. If c is somewhere between 0 and 1, the function is decreasing. And interesting things happen when c is equal to 0 or c is equal to 1. So let's go take a look at a basic exponential function. Okay. So change this to projector mode. Here is a basic exponential function. That's what happens when a is equal to 1. When a is equal to 1, the function is just equal to 0. Right, so let's move it up. Alright, so as you can see, here is what a basic exponential function looks like. It is an always increasing function. It increases quite sharply. And if I go between 0 and 1, I get a reverse of that. So greater than 1 goes up to the left, less than 1 but greater than 0 goes down to the right. And if I go below 0, this is what happens at 0. It's just 0, because 0 to any power is 0. Anything less than 0, and the graph stops to exist. I won't get into too much detail as to why that is. One of your assignment questions will deal with that. Okay. So some other interesting properties of exponential functions is this. One, the y-intercept is always going to equal to 1. Because mathematically, if you take anything to the 0 power, it's going to equal 1. So no matter what, you'll always know at least 1 point. And that's the y-intercept. So let me just change some settings here. 0 to 100. Okay. So if I let this play, notice that no matter what my a value is, the function never leaves there. At least the basic exponential function never leaves there. We can obviously move that point around as we see fit when we start transforming it, but we won't be doing that today. Let's change this to 1 in increments of 5. There we go. Right. There we go. This will give you a better idea because you can see the between 0 and 1 portion. So this point always constant for any basic exponential function. Always constant. Doesn't change. Always constant. Okay, another interesting point is that these functions don't actually have x-intercepts. the x-axis is what is an asymptote. If you remember from a couple lessons back, an asymptote is a line that is never reached. Well, for the basic exponential function, the x-axis is never reached. Never reached. Never reached. Never reached. No matter what happens. I zoom in constantly. Oh, and look, it never actually reaches that line. Never actually reaches that line. Okay. Jeez. There you go. Okay. So two characteristics of exponential functions. Y-intercept is always equal to 1, and x-intercepts are non-existent. Domain and range. For this type of function, domain is always all real numbers. X can take any real number. And range, well, range is basically anything greater than 0 for range. Because again, it can be any number, but it just can't be 0. And it never crosses the x-axis, never goes below 0. The exponential function never goes below 0. Again, that's partly because of our condition that a, or I should have written as c, a is always greater than 0. So f of x always has to be greater than 0. Okay. Now when you want to find new points in an exponential function, well, you always know at least 1 point. Well, I should just say you always know 2 points. The first point is the y-intercept, which is the first point. You always know what f of 0 is. That's always equal to 1. So you actually know 2 points. You know 2 points. So you know f of 0, which is equal to 1, and you can also know what f of 1 is. Because f of 1 is just whatever your base, so I forgot to mention, this number is called the base. This is the base. That's the base. And whatever the base is taken to the power of 1, that's going to equal the base. So you know at least 2 points. You know at least 2 points. Any other points can be found simply by using a table of values. So a table of values would be something like this. Seems kind of very elementary, right? So values of x, and then f of x. So 0, 1, 2. This would be a to the 0, a to the 1, a to the 2, and so on. 3 would then be a to the 3. So you just make a table of values and connect the dots that way. That's another easy way to I'm gonna put it, yeah, another way to graph these functions. Okay. Okay. So here's an example. Determine the value of c if the graph of f of x is equal to c of x passes through the following point. Well, this is sort of going a little backwards. Alright, so let's do the first one. So I know the following. So here is x, here is f of x. Our table of values goes 0, 1, 2, 3. So you know this is 1. You know this is going to be whatever c is. This is going to be c squared. This will be c to the power of 3. C to the power of 3 is supposed to equal 216. Okay, well there we can just take the cube root of 216, which we're solving for c. C is equal to cube root of 216, which is, I actually don't remember, 216 to the power of 1/3. No, that's not right. 260 to the 1/3 equals, this is 6. Now I know it's, so for the first one, we know C is 6. So f of x equal to 6 to the power of x. Okay. Now for the next one, I do the same thing. Oops. To do that, erase some of it, not all of it. That's okay. So x, so for the second one, 0, 1, 2, this is going to go to 4. So here we know c to the power of 4 is equal to 256. C will then be the 4th root of 256, which I believe is 4. Let me just check that. (256 to the power of 1/4). Oh yeah, it's 4. So here, f of x is equal to 4 to the power of x. There we go. So that's how we can determine the equation if we know at least 1 point. Again, because we know that as the exponential function goes up, we just take whatever the value of c is and we take it to the power of whatever x is. Okay. So that's how we can graph. That's how we can graph. Okay. Whoops. Going back this way. Okay. Example. Here's another one. Given the graph of a function, write the function. So here we can use, again, a table of values. Oh, it doesn't need a table of values. It's right on here. So this point here is 1, 1. This point here is 2, 4. I think this is enough information to find out what our function is. So here we go. F of x equals, let's write the table. Quick about it. X, f of x, 0, 1, 2. This is always 1. This is 1. This is now 4. Quite a big jump. Quite a big jump. Oops, I made a mistake. And this is actually not 1. This is actually 2. That makes more sense now. There we go. So it looks like it's doubling every time. So this will be f of x equals 2 to the power of x. Right. There we go. Then we can guess what 3 will be. 3 will just be 2 to the power of 3, so this will be 8. 4 will then be 16, and so on. And it goes on forever. Well, it can go on forever, yeah. Okay. So let's move on. Next. Yeah. Consider the following. This is an example. So suppose a virus spreads through a population according to the function f of x equals 1.5x, where x is the time in days. Let's graph this function. So graphing the function, a will be 1.5 to the power of x. So there's my function. Okay. Now, with this graph, we can answer the following questions. How many people will be infected after 5 days? How many people will be infected after 10 days? Well, let's take a look. I'll just make a graph x equals 5. Okay, so after 5 days, not too many people, only about 7.59 people will be infected after 5 days. After 10 days, well, let's change this to x equals 10, and quite a few people are infected after 10 days. So about 57 people will be infected after 10 days. And assuming this doesn't stop, well, we can keep going, and we can see, just say x equals 14 days. 4 days later, the number of infected people jumps to 291. After 15 days, 437. 16 days, 656. Let's say after 30 days, really big. After a month, assuming nothing changes. Wow. Okay. There we go. Ooh, wow. So if nothing gets done about this virus after a month, 191,000 people will be infected. And that's only if it increases the rate of 1.5. Most viruses tend to be a little more virulent than that. Take Ebola, for example. The Ebola, some people estimate the Ebola exponential growth to be much larger than that. So after a month, I think like good majority of that country will probably be infected unless something was done to stop it. Anyways, so that's one example of how exponential functions are useful. All right. Another example, or an assignment, I guess. Sorry, I mislabeled that. Here's your assignment for the day. Good luck with it. If you have any questions, there's lots of information out there about exponential functions and effectively how to just read them. All right, tomorrow we'll deal with transformations. Good luck.